Well, hello everyone, welcome back. So in this video, what we're going to do is we're going to go over just a couple types of rotational dynamics problems that you might come across. Right? There are a myriad different ways. These are just two examples. Hopefully they help. All right, so the first scenario we have is this. We have a rod of length 2r, which we see up here, that is free to rotate about this pivot point right here. Right? On the end, we have a force of 3F pointing up. And here, at distance r from the pivot point, we have a force pointing down, acting on the object. All right? We say that in this problem, we're going to say that the rotational inertia is going to be just I sub O, just I, doesn't matter. And we're going to be looking for an expression that represents the angular acceleration. Okay? So, where do we start? Okay, well, we know I, and we know we are looking for angular acceleration. The one equation that you know has both of those things is your net torque equals I times angular acceleration. So it's net torque equals I times angular acceleration. Okay, that's Newton's second law for rotation. All right, now, how do we approach this? Well, think back. How do we find our net torque? Well, that's going to be your torque counterclockwise minus your torque clockwise equals I times alpha. Okay, great. Now, another equation for torque that you know is that force times the moment arm times the sine theta. Right? The moment arm is from here to here, or here to here, and the forces are vertical. So the angle between these is going to be 90 degrees. Sine of 90 degrees is 1. I'm just going to leave out the sine. So here's what I'll write. I'll say force times r for counterclockwise minus force times r for clockwise equals I alpha. Okay. All right, now let's plug in the forces and the moment arms that are appropriate. Okay. This force is our counterclockwise. That's going to be this force here, right? Because without this force, it'd be allowed to rotate this way, which is counterclockwise. And for clockwise, it'd be this force. So let's plug things in. So our counterclockwise force is 3F, and your moment arm for that particular force is 2R. Okay. And for the clockwise, it says that your force is F, and the moment arm is R. Okay. Equals I alpha. Okay. So what I'm going to do is I'm going to just take a second. I'm going to erase pretty much everything that we've got. I'm going to leave the picture and the knowns, and I'm just going to rewrite that bottom line just so I have a little bit more space. Okay. Limited space on a tiny whiteboard. All right. So let's rewrite that. So we said that the counterclockwise torque was equal to 3F times 2R, and that we subtract our clockwise torque, which was F times R, and we said that was equal to I times alpha, our angular acceleration. Okay. So let's kind of multiply, simplify a little bit, and go from there. 3F times 2R will equal 6FR. FR will equal FR equals I alpha. Now I'm going to substitute that little O in, right? Because we said that our rotational inertia equals I sub O. So I sub O equals alpha. Well, we've got 6FR minus FR, which gives us 5FR equals I sub O times alpha. So do our subtraction and our little bit of division, and we can find our alpha to be 5 times F times R divided by I sub O. Okay. And there we go. Pretty simple. Okay, so there are several different types of ways this problem can be presented. You could have the pivot point someplace else with the forces on either side of that pivot point. It's all about making sure that you recognize which forces would cause a counterclockwise torque, which forces would cause a clockwise torque, making sure you subtract them, right? They might not give you just an I for your angular, your rotational inertia. They could give you some other expression that you need to plug in, right? It makes sure that you read the question and understand exactly what it is they're asking for and how they want that answer given. All right, so that was one example. Okay, let me give another example. Let me just erase the whole picture. It's going to be a new picture. So this time, what we're going to have is a cylindrical pulley. Okay, we're only going to see it on this kind of dimension here. That's fixed at its center. And for our purposes, we'll say that there's no friction between whatever's fastening that pulley to the table or to the ceiling or whatever, and the actual pulley, so that it's free to rotate without friction. Okay? And we'll say, let's have one mass of mass 3m coming off the left side, connected by a string, okay? And a mass of single m coming off the right side. Okay? It's all connected by the same string. Okay? This might remind you of some other questions that you've seen in linear dynamics, where we've had to find maybe the acceleration, right? This is an Atwood machine looking device. But now, since we're going to say this pulley has mass, we can't approach it in that same way. I'm not even going to take it as far as some other questions might in this particular example. But what I'm going to do is I'm going to also tell you that the rotational inertia is equal to 1/2 times m times r squared, okay, where that r is the radius of the pulley here. Okay, and I'm going to tell you that the mass of the pulley, m sub p, equals, we're going to make that just a big M. Okay, so the mass of these blocks is going to be a lowercase m. The mass of the pulley is going to be an uppercase M. Okay, for ease, if you want, I'm okay if you, for this time, leave it as m sub p. All right? Now, what are we going to be looking for? Well, I'm actually going to make this a two-parter, just because I can. The first thing I'm going to ask for is create an expression for torque. Okay, so let's create an expression for torque. Now, remember that torque we're talking about is our net torque. Okay, and that net torque is equal to your torque counterclockwise minus your torque clockwise. All right, so just like in the previous problem, our torques are caused by the force of being applied to the object times that moment arm. Let's say these masses are hanging vertically, so that force is due to gravity from each of these. Okay? And the moment arm will be from that axis point to where the force is applied, so from here to here. Okay? Since we're going to say that it's from here to here, that's horizontal. Same thing on the other side. Gravity acts vertically. Angle between horizontal and vertical is 90 degrees. Sine of 90 degrees is 1. So I'm not going to write the sine theta for this particular problem. Okay, so net torque equals your torque counterclockwise minus your torque clockwise. Which force would cause a counterclockwise torque? Well, it's going to be this one right here. Okay, so that's going to be your force of gravity from your 3m. So I'm going to write FG3 times that moment arm, which is your radius here. There are no other forces causing counterclockwise torque, so let's move to clockwise, which is going to be the force of gravity of this single m. So we'll just do FG, I'll say sub 1 because it's just 1m, times r. Okay. Let's expand and then simplify. Force of gravity is your mass times acceleration due to gravity. Well, the mass of this object is 3 lowercase m. 3 times lowercase m times your acceleration due to gravity, g, times that moment arm, r, minus the mass of this object, which is just a single lowercase m, times your acceleration due to gravity, times your radius, r, that moment arm. Okay. Now, simplifying that out, we have 3mgr minus 1mgr, which yields 2 times m, lowercase m, times g, times r. And there is our expression for our torque, our net torque. Good. Now, I told you this was going to be a two-parter. So, the second part is going to be asking for an expression for the angular acceleration. Alrighty? So, we have a net torque, which I'll substitute that in right there. We said that was 2 lowercase m g times r, and we're looking for acceleration now. Okay. We have a net torque. We have an expression for our rotational inertia. Looking for our angular acceleration. Great, not a problem, because we know the net torque equals your rotational inertia times your angular acceleration. We have an expression for this. We have an expression for this. Let's plug those things in and solve for our angular acceleration. Okay, so we said that our net torque was 2 times lowercase m times g times the radius, our moment arm, r. And we said that your rotational inertia is 1/2 times the mass of the pulley, which we said is uppercase M, times r squared. So let's plug that in. Okay, so we have 1/2 uppercase M, because that's the mass of the pulley, r squared, okay, times alpha. Right, so here's our expression so far. Now, we can divide this whole expression right over here. So we'll say alpha equals 2 lowercase m gr divided by 1/2 uppercase M r squared. Just try to make that more uppercasey. Okay. Now, we can do some substitution and some simplification here. We have 1r here and an r squared here, so we can cancel out that r and one of those r's. Okay. We cannot cancel out these m's. They are different m's. Remember, this is a lowercase m that represents the masses of these, and this is an uppercase M of the mass of the pulley. We cannot cancel those out. Okay. Then we have 2 divided by 1/2, so it's effectively 2 times 2. So I can simplify this to be 4 times lowercase m times g divided by uppercase M times r. And here's our expression for our angular acceleration. Right? Now, they could ask you for an expression for linear acceleration, at which point you would say, all right, I'll try to make a little recall bubble up here. Remember that your angular acceleration equals linear acceleration divided by r. Right? You would just plug a divided by r into your alpha and just kind of simplify from there. Right? And kind of go from there. All right, and then you'd also need some Newton's laws. But like I said, we're not going to really get into that at the moment. All I wanted was your angular acceleration. All right, and that's it for now. See you later.